start this recording. I was trying to decide what's more important. You guys or the people who are online? You guys. Hear that, people online? No. Everyone got a handout with the properties of exponential and logarithmic functions. It's a preview of what we're doing today. And if you didn't get an assignment or a copy of just this extra formula sheet last day, make sure you grab one. You only need this formula sheet for the well, you probably don't even need it for the volume of a cylinder and a sphere for the assignment. And then the rest is just extra because I had room to print. All right. So remember, you can work in groups for the assignment. Just hand it in as a group, obviously. Whatever mark you get, you split amongst all of you who's in that group. If you don't want to work in a group, that's totally fine. That's allowed, of course. It's just meant to make it easier. Okay. All right, now that I'm finally all set up here, I'm all discombobulated. Let's see here. Let's start a new note. So we started an example last day that we didn't have time to finish. Where can I steal that from? Probably here. Oh, man. Should just be a mute button. All right, so here's the example from last day, which I'm assuming you have. We were going to show that g of t minus 2 over 2t minus 1 is 1-to-1 analytically, right? So we went through and we just showed that if we take f of a equal to f of b, we're able to prove that a equals b. Right? So that's how we prove that something's 1-to-1. Sometimes it's easier than other times, right? But usually it's pretty straightforward, right? So that's how we show that something's 1-to-1. And then 1-to-1 just means that it takes one value of x and it maps to one value of y, right? And so it's just 1-to-1. The reason we care about it being 1-to-1 is because if it's 1-to-1, it's invertible, right? Which means that we're able to find the inverse. So if you're working on the assignment, question 7 on the assignment is from the inverse section, right? And so that's the one that we're going through today, or now, I guess. And then you'll be able to do all those questions on the assignment. Okay. One thing that we can do, if we don't want to check that something's 1-to-1 by checking that f of a equals f of b means that a equals b, right? Then we can graph it and we can just make sure that it passes the horizontal line test, right? So if we draw horizontal lines, then these lines can only pass the graph at one single point, right? And so I think we confirmed it. And then we were about to find the inverse. So let's see here. So we showed that it's 1-to-1. And so we just took g of t, g of a, and g of b. We just use a and b as our variables, right? Plug them in, they look the same. And then we go through and we solve. And finally, it flushes out that a equals b. What a relief. All right. And so g of t is 1-to-1, and therefore it is invertible. Okay. Here's my crappy drawing, right? But this is what the graph of it looks like, right? This blue line here and this blue line here. We've got these asymptotes, horizontal and vertical asymptotes that we haven't really talked about, right? But if we draw horizontal lines, then these lines only cross the graph at one single point for the entire graph. So, and I think that's where we ended off. So let me just copy because you have this written out already, but oh, hey, I thought I started something. Okay. So example continued. Continued. Right, we have g of t was what? T minus 2 over 2t minus 1. Right. We showed it's 1-to-1 and passes the horizontal line test, which I'll just write HLT, last day. So now we're going to keep going. We're going to find the inverse, right? So the inverse is the function that undoes another function, right? And so we've seen simple cases like the inverse of x is 1 over x, right? But it's not always just 1 over whatever, right? It's a little bit more, it's a bigger deal than that. Okay, so it's the function that undoes another function. And then, this was a while ago, I guess, last week, confirm it's the inverse using function composition, right? And so we had that rule that says that if we have a function composed of the inverse, it'll just return x. And if we have the inverse composed of the function, it should also just return x, right? So regardless of what composition you're using, and we'll do both, it should just return x. And then we're going to look at the domain and range of the original function as well as the inverse. Yikes. All right, here we go. Feels like a long time ago. So last day, we talked about the steps for finding the inverse, right? So what you're going to do is you're going to write out your function, and then you're going to swap your x's with y's and your y's with x's. Right, and then you're going to solve for y, and the solution will be the inverse. Okay? So to find the inverse, this is kind of review, I guess, but to find the inverse, we write y equals g of t. Swap x's with y's, and of course y's with x's, and then solve for y. The solution is the inverse. So we're going to start with y equals g of t is t minus 2 over 2t minus 1. I guess we can rewrite this as x's to match my description, but it doesn't matter. So now we're going to have, do you guys like t's or x's? Doesn't matter. X's, you got it. X minus 2 over 2x minus 1. Same deal. So now, what we're going to do is wherever I see a y, I'm going to write an x. So I get x is y minus 2 over 2y minus 1. And then wherever I see an x, I'm going to swap it with a y. And now I'm going to solve for y. So now solve for y. So kind of start unraveling this thing. And so I'm going to multiply both sides by 2y minus 1, right, to get rid of that fraction. And so I get x, I guess, I don't want to have to deal with this line break. Oh, well, so I'll start fresh here, 2y minus 1. Multiplying both sides by 2y minus 1, remember to put it in brackets, right, because they all have to hang together. So we've got x times 2y minus 1 is y minus 2. Is there like a hissing sound? Oh, like what is that? So now we can expand these brackets because remember the goal is to solve for y. And so if we're solving for something, we want to get y on its own on one side and then everything else on the other side. And so if we expand these brackets, it's going to be easier to get at that y inside the brackets. So we get 2xy minus x is y minus 2. And same deal, right? Trying to get y's on one side, everything else on the other side. So I'm going to bring the y on the right-hand side over to the left-hand side, and I'm going to bring the x on the left-hand side over to the right-hand side. Really hoping I kept my lefts and rights straight, but that's all right. I think you know what I mean. So, and I'm going to do it in one kind of switcheroo. So I get 2xy minus y is negative 2 plus x, or x minus 2 if you prefer. Now, I've got this common y that I can factor out, right? And that's good. That's a good thing because then I can divide both sides by 2x minus 1. Right? Looks like this. So I can rewrite this as y times 2x minus 1 is minus 2 plus x. Right, just factoring out that common y. Now I can divide both sides. So I get y is negative 2 plus x, or x minus 2, it doesn't matter, over 2x minus 1. Therefore, g, remember how we denote the inverse with a to the power of negative 1? G, the inverse of g of t is negative 2 plus, and now I'm going to rewrite this in terms of t just because they were in terms of t before, right? But we said, no, we like x's, and that's fine. Over 2t minus 1. Okay. Clean this up a bit. So there's the inverse. It looks similar to the original function, right? And it will always kind of look a little similar, right? Or not always, but usually, right? And so you have to be really careful when you're kind of solving for y, right? That you're keeping all your negatives straight and all your multiplying and dividing. Okay? So now just to double check that we have the right inverse function, right? We have to use function composition. And so now use function composition to show that g inverse of t is the inverse of g of t. Yeah. So what we're about to show is that G composed with the inverse of G and T or X. X again? Like I said, it doesn't matter. X? I didn't hear any yays or nays. So we have to show that G composed with the inverse of G equals X. Right, so in the end, we're going to end up at X, and that the inverse composed with G, the original function, is also X. So we're doing a little bit of practice, I guess, with function composition, but this is the reason that you had to learn function composition anyways. And so, or one of the main reasons is to be able to check the inverse and prove that you've found the inverse. And so here we are. All right, let's start with G composed with the inverse of G of X. And so we've got the original function, and we're going to plug in wherever we see an X or a T, right, wherever we see a variable, we're going to plug in the inverse of G. So we can rewrite this as G of G inverse of X. Oh, that's allowed. So now, wherever we see a T, I guess, in the original function, we're going to replace it with just the inverse of G. And so we've got, what was our original function? Keep forgetting it. T minus 2, which we're going to have to rewrite as G inverse of X minus 2, over 2T minus 1. So 2 times G inverse of X minus 1. I just realized that I should check. No complaints, though, and I'm not on mute, so phew. I don't want to have that happen again. Where I'm talking away. All right. So now that I've got the G inverse of X, I'm going to replace it with the actual inverse of X, right? And then it's a matter of simplifying. And at the end of the day, we know we're going to end up with just an X. And so it will simplify down, right? Otherwise, we found the wrong inverse, or something went wrong with the inverse. And so we replace the G inverse of X with -2 plus X in this case, right? We'll use X as our variable, over 2X minus 1. So I'm going to take a little bit more room here. -2 plus X over 2X minus 1. Clean that 2 up. Minus 2. Times 2 over same thing, -2 plus X over 2X minus 1. Minus 1. So don't be stingy with the brackets or even the space, right? Because what we're going to end up with is we're going to have a fraction over a fraction. And so we're going to need to have a common denominator, right, on both of these guys. And then once we have a solid fraction over a solid fraction, then we can flip and kiss and simplify it even further. Right. So looking at the numerator, right, the top one, what do we have to do to get a common denominator here? We just have to multiply 2 by 2x minus 1 over 2x minus 1, right? So I always use the trick of multiplying. So I want 2 to be written as something over 2x minus 1. So what I do is I just take 2 times 2x minus 1 over 2x minus 1. 2x minus 1 minus, or over 2x minus 1 is just 1, right? That's just going to cancel out. So I'm multiplying by 1, doesn't change anything, right? And so that's allowed. And so what we end up with here is we get negative 2 plus x over 2x minus 1 minus 2 times 2x minus 1 over 2x minus 1. Making sure that you keep them inside the brackets, right? Because you don't want to lose those brackets and forget to expand something. That's the numerator. And I'm dealing with a page break here, so I'm going to shift this down a little bit. So we need more room. There. Oops. Now I'm going to deal with the denominator in much the same way, right? I'm going to multiply that minus 1, that last minus 1, by 2x minus 1 over 2x minus 1. If you want to, you can expand out the 2 times negative 2 plus x. Which would you prefer? Common denominator. Expand a little bit. Let's expand it a little bit. So we get 2 times negative 2 is negative 4 plus x times 2 is 2x over 2x minus 1 minus 1. Now in the next step, I guess I could combine the common denominator up top in the numerator, but yeah, sure. It'll be one step ahead of the denominator. How about? So we get negative 2 plus x, not 2. Minus 2 times 2x minus 1 all over 2x minus 1. Actually, I will put brackets. That's the numerator. I still need to get the denominator over a common denominator, right? And so I've got negative 4 plus 2x over 2x minus 1 minus 1 times, times 2x minus 1 over 2x minus 1. And then now I can put that denominator over a common denominator. So many numerators and denominators. Oy. I'm going to leave the top as it is. So negative 2 plus x minus 2 over 2x minus 1. You definitely could simplify here, but I'm going to focus on cleaning up the denominator for right now. Just as a little hint, I guess, if you're dealing with a fraction over a fraction, then it's pretty common practice to make the main divisor here, or the main kind of line, I guess, a little bit longer, just to show, so that you can keep track of, okay, well, this is a fraction over another fraction, right? And so you make that line a little bit longer. I realized I'm doing it, but I didn't tell you that I'm doing it. So Now we've got this common denominator, so minus 4 plus 2x minus, do I keep the 1? Sure. 1 times 2x minus 1 all over 2x minus 1. Okay. All right. So now I'm going to clean up these numerators in both the numerator and the denominator, right? So that I don't have to lug all this stuff around. And yeah, you definitely could have cleaned it up at any point, as long as you're careful. And so we've got negative 2 plus x, there's nothing I can do there, but then I've got minus 2 times 2x minus 1, so I can expand that in. So I'm going to have negative 2 plus x, doesn't need brackets around it anymore. Okay. So there's nothing going on, no multiplication. Minus 4x plus 2. After you bring in that minus 2. Still over 2x minus 1. And then dealing with the denominator, I've got minus 4 plus 2x. Nothing happens there, so minus 4 plus 2x. And then I can expand the minus 1 in, so negative 2x plus 2 plus 1. And again, over 2x minus 1. Things simplify kind of nicely here, right? Because we've got minus 2 plus 2. That's going to go away, right? And then we've got x minus 4x, right? So that's, we've got negative 3x. So let's put that out. So we've got negative 3x over 2x minus 1. And then down here, we've got 2x minus 2x, so that's going to go away. And then we've got minus 4 plus 1, so minus 3. Negative 3 over 2x minus 1. This is a lot easier to deal with, right? Because now, remember, the rule for dividing fractions is you flip the denominator and then you can multiply the fractions and they just multiply straight across. And so we've got negative 3x over 2x minus 1 times 2x minus 1 over minus 3. The 2x minus 1, so they're going to cancel. And also, negative 3 over negative 3, that's going to cancel. But I'll write it out so it's nice and clean. Negative 3x over negative 3 is x, right? Because that's going to go to 1. Phew. If you did go through all that trouble and you did not end up at x, then that's bad, right? Then you either, well, did your function composition incorrectly, but probably not, because it's just stuffing a function inside another function. So then it's more likely that your inverse was wrong and you have to go back and check your inverse, right? And so what's nice is you know what your answer is supposed to be for these things. Right, so it will reduce down. It's just a matter of plugging through it. Any questions before we do the reverse of it? It's going to look similar. All right. G inverse composed with G of X is the same as the inverse of G of X. Right. So same idea. We take G of X and we plug it in wherever we see an X or a T or whatever variable in the inverse. Okay, so I'm gonna just do a little recall. The inverse of X was what? Because I keep forgetting. -2 plus X, oops. -2 plus X over 2X minus 1. And G of X was X minus 2 over 2X minus 1. Can even put those in brackets if we want.
A quick question.
Yes.
Is there a case which would satisfy one would be X and one wouldn't be?
No, as a rule, the inverse has to satisfy both compositions. Yeah. So we're just doing this for fun, guys. All right, same deal, right? It's a little bit more familiar now. So here we go. We take the inverse of G, and wherever we see an X, we're going to plug in G of X, and then we're going to plug in G of X. So we're not left with any functions. All right, the inverse is -2 plus X, where we're going to write just G of X for now, over 2X, where we're going to write just G of X minus 1. Now, wherever I see a G of X, I'm going to replace it with X minus 2 over 2X minus 1. So I get -2 plus X minus 2 over 2X minus 1. And remember, I'm not being stingy with space nor brackets. I say that I could throw some more brackets on here if I wanted. Keep them all tight. Okay. And then I've got 2 times G of X, which I'm going to replace with X minus 2 over 2X minus 1. And then minus 1. It's then going to end up looking the same, right? Very similar. Same idea, you have to get a common denominator, and this is going to be, as soon as you're dealing with fractions in any of your functions, right, that's what you're going to have to be dealing with, is just common denominator, right? Simplify the top, simplify the bottom, and then flip and kiss to multiply those fractions, and then it's going to cancel out. So here we go. We have to get the common denominators again. And so we've got -2 times 2X minus 1 over 2X minus 1 plus X minus 2 over 2X minus 1. Maybe not taking my time as much as last time, right? But same thing. And now I have to get the common denominator in the denominator. So I get, well, I guess I can multiply out. The 2 just multiplies the numerator, right? The 2x minus 2 becomes 2x minus 4. Buckle up. I did it all in one go.
Oh, wait, no, sorry, I just thought you. Oh, yeah.
Where are you? Good?
I thought you, yeah.
Okay. I'm in the, yeah. All these get a little sticky.
You did that, like, towards.
Yeah, so what I did this, I brought this guy in here and put it over 2x minus 1.
That's the bottom.
Yeah.
For the top, though. Sorry.
Here?
Yeah.
Oh yeah, so I did -2, I'm putting it over 2x minus 1, so I have to multiply by 2x minus 1 over 2x minus 1.
You did that to one side?
Because this one's already over 2x minus 1, so I'm just forcing it to have the same denominator, right? By multiplying by 1, right? Because this would cancel to 1, right? So -2 I'm not changing, but that's how I'm going to get that common denominator.
That doesn't, like, you don't have to change the x minus 2.
This one?
Yeah.
No, because it's already over 2x minus 1.
You don't multiply the whole term by just like make like 1 negative or 2 x minus 1 over 2x minus 1. Because it's all on the top. I don't understand why.
Okay, so here, bring it down a little bit, right? We were here, and then we came here, right? So I want to have this -2 over 2x minus 1, right? X minus 2 is already over 2x minus 1, so I don't have to do anything. But what I have to do is I have to multiply -2 by 2x minus 1 over 2x minus 1. Because if you think of this as 5 over 5, 5 over 5 is 1, right? And so it's just multiplying by 1, but it's forcing it to be over 2x minus 1. But you don't have to do anything with x minus 2 because it's already over that 2x minus 1. And then I'm about to do the same thing over here, right? -1 times 2x minus 1 over 2x minus 1.
So you multiplied that through, but you're not going to do it for that one.
Because I'm getting the common denominator.
But you can't just multiply it through, just keep the common denominator. So
Mm.
you can't just have like -2x plus 1 without doing that.
No, you can't. Do you mean here?
Yeah. So
Yeah,
I can't just like put it through and just like skip that.
Yeah, so you have to have this -1 has to be over. Because that's the property of adding and subtracting fractions, is they have to be over the same thing. All good to here, I guess? Sort of? Yeah. It looks the same, just a little bit backwards, I guess. So now I'm going to expand and simplify this thing a little bit. So I get -2 times 2x is -4x. -2 times -1 is +2. Plus x minus 2. Brackets aren't doing anything, so I can just ditch them. All over 2x minus 1. And then simplifying the bottom, I get 2x minus 4. -1 times 2x is -2x. -1 times -1 is +1. All over 2x minus 1. Ooh. So again, I'm going to simplify the numerators in both of these. And so I get, let's see here, plus 2 minus 2, that goes away. And then minus 4x plus x puts me at minus 3x over 2x minus 1 over, and then 2x minus 2x, again, those go away. I've got negative 4 plus 1 is negative 3, so negative 3 over 2x minus 1. Yes?
Okay, so when we have the initial equation,
Mm-hmm.
we wrote like the x minus 2 over 2x minus 1 minus 2.
Yep.
On the numerator, and then the, like before we've done any foiling. Or
Stop me.
Yeah.
Here.
Yeah. Like, so I'm confused. For the top, we had to times it by the 2x minus 1.
Mm-hmm. This guy?
Yeah.
Mm-hmm.
So then we had that times 2x minus 1 over 2x minus 1.
Yeah.
But why do you not have to do that for the 2 in the denominator? That one.
This guy?
That guy right there.
Well, because it's multiplying. So we only have to do it if we're adding or subtracting with fractions.
Okay.
Right, and so if we're adding or subtracting and we've got one of them as a fraction, you have to have a common denominator here and here. Right? If we're multiplying, it's safe. Multiplying or dividing, but multiplying mostly, then we can just pull it in and it can just stay over 2x minus 1. That's allowed. But as soon as we're adding or subtracting, then we have to have a common denominator. Nice. All right. We're so close, you guys. Here we go. Fraction over fraction, we flip and kiss. And we do negative 3x over 2x minus 1 times 2x minus 1 over negative 3. 2x minus 1 cancels with 2x minus 1 because we're multiplying. And negative 3 cancels with negative 3. And I'm left with, drum roll please, x. All right, we did it. We showed that the inverse that we found is actually the inverse of G. You do have to prove that both the compositions work, right? So you can't just do one of them. I want to see both of them because I am very sure. Oh, show that the given function is 1-to-1 and find its inverse. Great, you know how to do that. Check that f of a equals f of b means that a equals b, right? That's checking that it's 1-to-1. Then find the inverse, swap your x's and y's and solve for y. And then that's your inverse. Check your answer algebraically using function composition and then graphically using Desmos. I don't actually care for you to do on your own, I guess. Make sure you make a note of that. We'll do it, but and then verify the range of the function is the domain of its inverse and vice versa by clearly stating the domain and range of the original function and its inverse. Great. Guess what's up next, guys? Let me scroll way up to the rest of the question here. All right. Confirm it is the inverse using function composition. We did that. State the domain and range of the original function as well as the inverse. Yeah. Let's check. Let's just graph these. Let's have a little Desmos break. How about that? So I'm just going to plug in g of x, because remember, Desmos only likes x's and y's. So we've got, okay, so x minus 2. And I have to divide it all, so I have to put brackets around the x minus 2, divided by 2x minus 1. There's my original function. And then the inverse was, all in brackets, -2 plus x divided by 2x minus 1. What? They look the same. Yeah, they do. Why? I don't think we talked about it last day because I'm trying to not do so much graphing. But the inverse is going to be a reflection around the y equals x line, right? So it's always going to be kind of a flip-flop, right? And so, and that's what we're seeing here. But the original function also had that mirror image, right? And so they look the same.
How does it know it's the inverse? Is that exactly the same? Like your
well,
how does it know that's the inverse?
Because one is green and one is purple, I guess.
No,
I don't know.
How does it know how to that you're asked, like you have to say you're looking for the inverse?
No, I plugged it, like I plugged in what we found to be the inverse.
Oh, okay.
Right. So it doesn't identify it as the inverse. But if it's a mirror image, if it is the inverse, it will be a mirror image around the y equals x line. Yeah, exactly. So, oh yeah, x minus, oh yeah,
You just
the inverse of it. I just did, yeah. I'm picking up what you're putting down. Yeah, you're right. So the inverse is itself, I guess, to undo itself. 2x, yeah. And I was not paying attention, so I didn't even. All right. We did that. Okay, so the domain, well, actually, let's write out our original functions again, because as you pointed out, they're the same. So it's not even negative signs, just swapping them. No. Let's see here. So we've got g of t was t minus 2 over 2t minus 1, and g inverse of t was, but as we pointed out here, or as you guys pointed out, this is just t minus 2 over 2t minus 1. I must add my blinders on or something. Doesn't matter. We treat them all the same, right? So they're the same function. Wah, wah. One undoes the other, which is weird. No, no, they won't. They won't. there's going to be like, yeah, so you might have kind of a curve like this, and then the inverse would be the reverse of it. Right. But anyways, I can't believe I didn't see that. But anyways, all right. As a rule, the domain of the inverse is the range of the original function, right? And the domain of the original function is the range of the inverse, right? And so if you're finding the range, typically, so up until now, what we've been doing is we've just looked at a graph where we just have an idea of what it looks like. Can it take on all values from negative infinity to positive infinity? Or maybe it's has to be greater than 0 or something like that, right? But now we know that, okay, if I'm able to find the inverse and find the domain of the inverse, then that's the range of my original function. Okay? And so to find the range of a function, g of t, for example, we find the inverse, g inverse of t, and the domain of g inverse of t is the range of g of t and vice versa. Okay, so that's kind of a hard rule for if you have to find the range, right? Then what you would do is you would find the inverse, which you know how to do now, and find the domain, because that's easier to do, right, than to try to think of, okay, well, what values can this y take on, right? And so, because for the domain, we've got these rules, right? We can't divide by 0, so anything that makes us divide by 0, that's out of the domain. We can't take the square root of a negative number. Anything that makes us do that is out of the domain, right? And so we've got these rules for figuring out the domain, and it's just typically easier to deal with. So the domain for g of t, well, if we just look at g of t, it says that, well, we're dividing by 2t minus 1. So what we say, I'll do that down here instead. G of t is t minus 2 over 2t minus 1. So 2t minus 1 cannot equal 0. Solving for t, right, to figure out what t we need to pull out, we get 2t cannot equal 1, and so t cannot be 1/2. So the domain of g of t, if we want to use interval notation, is from negative infinity up to 1/2, not including 1/2, and then starting back up at 1/2 up to infinity, right? All other values are a go. Okay. Let's look at the domain of the inverse of g of t. The inverse of g of t was also t minus 2, we said, over 2t minus 1. So again, 2t minus 1 cannot equal 0. So we know, I'm not even going to do it. T cannot be 1/2. So the domain of the inverse of G is also negative infinity to 1/2, and then starting back up at 1/2 up to infinity. Okay. Therefore, by properties of the inverse, the range of G of t is the domain of the inverse of G of t. And, oops. And the range of the inverse of G of t is the domain of G of t. I missed the word, domain of. Okay. So you really only have to find the domains, and then you'll have the ranges, right? But you have to find the domain of the original and the inverse, and then you'll have the ranges. In this case, yeah. But it means that the domain is the domain of one is the range of the other, and vice versa. Exactly. All right. Any questions? It was a long example. They're long problems. They're fun though. Kind of. Oof, I make you do 3 of them, huh? Well, that's cruel. You'll be pros. All right. So that's the end of chapter 5. So we're going to start chapter 6, which I think you'll be happy to learn is exponential and logarithmic functions. No? No one's thrilled. Okay, well, I was happy to learn that it's exponential and logarithmic functions. So I did save us some writing by printing this out, because I was like, well, these properties, yeah, they're important to have and they're important to go over. Are they important for us to write out? It was going to take us forever. And so I just cheated. And I might do the same for some other properties if you guys are okay with that. I've just stolen these from the textbooks, so. Luckily, it's a free textbook, so I feel like I'm off the hook. No copyright or anything. All right. Any questions, though, before we get going with chapter 6? Oh. All right. Chapter 6. Exponential. Oh, exponential. And logarithmic functions. Logarithmic functions. So we're going to start in section 6.1, and then we're going to work all the way through to 6.6, I want to say. Not today, obviously, but that would be impossible. Well, not impossible. We'll start with exponential functions. So up until now, right, we've seen things like x cubed and x to the 1/2 and things like that, right? And so up to this point, we have looked at functions. We've looked at functions such as x to the power of 3, x to the 1/2, x to the -2, etc. Where the variable x is in the base. Exponential functions are when we have the variable in the power. So exponential functions are of the form f of x equals b to the power of x, where the base b is constant. Oops. And the exponent, x, is the variable. And the exponent, x, is the variable. Fair enough. So just as a formal definition, I'm going to look the same, but an exponential function, because it puts a few restrictions on b. An exponential function is of the form f of x equals b to the x, where b is a real number. B has to be greater than 0. Right, and so that's kind of interesting, right? Because we can't, what that says is we can't have a negative base. And b cannot be 1. Right. Mostly because 1 to the power of anything isn't that interesting, right? It's just going to be 1 times 1 times 1 times 1 times 1 times 1 times 1 is just 1, right? And so it's not very interesting. So we put that restriction on and say that b cannot be 1 because that would give us a constant function. The domain, oops. The domain of an exponential function is from negative infinity to positive infinity. Throw a little box around that, why not? So let's consider something kind of basic like f of x equals 2 to the power of x in Desmos, just to see what it looks like. So 2 to the power of x, nothing crazy here, exponential function base 2. Ditch that, ditch that. 2 to the power of x looks like this. So we've got the domain, we've got all real numbers from negative infinity to positive infinity. We see this, and what we'll soon realize is that this is kind of a token characteristic of an exponential function, is that it looks like it follows kind of the line or the x-axis here, and then it takes off. But it does span all the way to infinity, just kind of slower. Shooting up. So let's see if I can do that justice here. Probably not. I'll use a different color because I have to be so close. I've already mentioned it, but this is the first time that we're actually going to write it out, I think. When the line goes and it approaches the x-axis, but it actually never touches it, we have an asymptote, a horizontal asymptote in this case. And so now we're going to start talking about asymptotes where the line of the graph gets really, really close to a spot, but it can never actually touch it, even at infinity. So we see that as x approaches negative infinity, oops, that's not infinity. As x approaches negative infinity, the graph approaches the x-axis. But it will never touch the x-axis. This is a horizontal asymptote. If we look the other way, right, as x approaches positive infinity, we see that eventually, because we've got this kind of incline this way, right, as we go to infinity, 2 to the power of x will also approach infinity. And so as x approaches positive infinity, we see that 2x, or 2 to the power of x, sorry, also approaches infinity. These are, in fact, general properties of exponential functions, right? So it doesn't matter what base we have. These are in fact general properties of exponential functions. This is where I opted out and decided to just steal it. So this is the printout that you guys have. I'm just going to put it in our notes. Got all grainy somehow. I think I might have photocopied and then photocopied again and then scanned it. How you get this low quality. I don't know. But anyways, right, and so now we can talk about these general properties of exponential functions. Are these going to be good to know? Yes, absolutely. Right? Do we need to write them down? Probably not. Right, so, oh yeah, you didn't get a, did you guys get a copy? Everyone else got a copy though, right? I think, yeah. It looks like this. And so we've already talked about the domain of an exponential function is going to be for negative infinity to positive infinity. That's always going to be true as soon as we have an exponential function. So that's nice. And then the range, it's never going to drop below 0, right? So it's going to go from 0 to positive infinity. Not including 0 because it's never actually going to touch that x-axis, right? And so we've got round brackets. The point 0, 1 is on the graph, right? And y equals 0, that's the x-axis, right, is a horizontal asymptote. So we've already talked about that. Just looking at the graph, right, we see that there's a slight decline and a slight incline, or a quick incline, sort of. And so if we had to do the horizontal line test, right, to check if it's 1-to-1, it would pass, right? We could also, if we had to, we don't have the tools quite yet, but we could check that f of a equals f of b means that a equals b, but like I said, we don't quite have the tools there because the x is in the power, right? So that's true. But just as a rule, we know that as soon as we have an exponential function, it is 1-to-1, right? And so now you don't actually have to check it anymore because that's a property of the exponential function. And so that's why it's nice to have this here, right? Because if it's 1-to-1, therefore, f is invertible, right? That's why we care about things being 1-to-1, is because we actually just care about knowing if it's invertible or not. Right? So f is 1-to-1, and the take-home message there is that f is invertible. Spoiler alert, the inverse is the logarithmic function, right? And so they're the original and the inverse, I guess you could call them, right? But we'll start with the exponential function because it's the original. Okay. The exponential function behaves a little bit differently depending on if b is greater than 1 or if b is between 0 and 1. Remember, b had to be greater than 0, right? We can't have a negative base. So it behaves a little bit differently. Greater than 1, we have this activity that we saw, right? We had 2 to the power of x, 2 is greater than 1, and so we've got this graph that we saw earlier. It crosses the y-axis at 1, right? So 0, 1. Same thing if b is between 0 and 1, then again, it crosses the y-axis at 0, 1, but it's going the other way, right? But same properties, right? It approaches the x-axis, but actually as x is going to positive infinity now, And so you've still got that horizontal asymptote regardless of which base you have, right? But it's going to be going in different directions. So this is just kind of general information to log, right? I'd say the most important kind of take-home message is that it's one-to-one, right? And therefore it's invertible. But it's also good to know that it never drops down to a negative y, right? So y has, or the range has to be from 0 to infinity, and the domain is always from negative infinity to positive infinity. Look at all these. I cut a whole page. Aren't you guys glad? I'm saving it for later. But yeah, good, good, good. So we've seen 2 to the power of x, right? There are some common bases that we're going to look at and some less common that we'll work with, but we're going to focus on just 2 really common bases. 2 to the power of x is not one of them, actually. 2 to the power, so base 2 is mostly for computer science, right? When you've got binary things, zeros and ones, right? So they deal with 2. So exponential functions base 2 a lot. But for the rest of us, we deal with base 10 and base e, right? So those are going to be our go-to exponential functions. We have already seen f of x equals 2 to the power of x. The exponential function base 2. Exponential function base 2, which is important in computer science, I will say that. In computer science, but we will focus on 2 other common bases. So the first one is base 10, which is called the common base. Called the common base. This is usually for things of intensity, so like sound, earthquake, acidity, right? And so that's when we've got base 10. And so probably, I mean, for you guys, especially if we're talking acidity, right, that one might have perked your ears a little bit. Right, and so important in the study of intensity, right? So things like sound, earthquakes, acidity, acidity, too many, acidity, etc. Second one is base E. Now, E is a number, and E is approximately, and you've got it on your calculator, if you go, it's over the times 10 to the power of X button in red, and so you have to do the alpha button, and then E, and then equals, and then it'll give you the approximation 2.71828. There's a song, but I can't remember. 2.718. Anyways. So E is 2.718. Press alpha. Oops, alpha. Press alpha, and then the times 10 to the power of X on your calculator. Oh, do you have an E to the X button? Yeah, nice. Yeah, so regardless of what calculator you have, it will have an E to the X button, so you might have to do E to the 1 or something like that. But, this is called the natural base. And it's important for modeling growth curves. Typically. Actually, the natural base, it's kind of important to a lot of things. And so it's kind of a go-to for a lot of fields. Like in stats, for example, we only work in base E. And so the natural logarithm, which we'll talk about, but also the natural exponent. But anyways, sounds like you guys are more base 10 folk. So here we go. Let's do an example. What? We haven't learned anything. I know, crazy, right? We've learned so much. That's the problem. According to Newton's law of cooling, which I can only assume that we're going to revisit in more detail, but this is kind of a brief introduction. The temperature of coffee oops, denoted by T of T, capital T of T, in degrees Fahrenheit, T minutes after it is served, can be modeled by T of T equals 70 plus 90 e to the negative 0.1 t. An exponential function with a natural base e. Nice. So someone, well, I guess Newton decided it was really important to figure out a function for how quickly things cool off, right? So you've got boiling water, you put it out into room temperature, how quickly does it cool, right? So you've got a function like this where you've got the initial or the room temperature, and then where it starts and then it cools off, right? And so, all right. So we've got this law of cooling function. Part A, find and interpret T of 0. Well, we can find it easy enough. T of 0, we just, wherever we see a T, we're gonna plug in 0. So we've got 70 plus 90 times e to the power of 0.1 times 0. So we get 70 plus 90 times e to the power of 0, right? Negative 0.1 times 0. That'll behave as we expect it to. It's just 0. Anything to the power of 0 is 1, right? But you can check it on your calculator by going e, so alpha, and then the times 10 to the x button, and then to the power of 0, and you should just get 1, right? That's because, as a rule, anything to the power of 0 is 1. Except 0, I guess. But, yeah. So we've got 70 plus 90 times 1, just to be clear, is 70 plus 90, which is 160. So T was the number of minutes after this coffee's been served, right? And so to interpret T at 0, right? So at T equals 0, which is 0 minutes after serving, the temperature is 160 degrees Fahrenheit, right? Because the units were degrees Fahrenheit. Good. Part B, we're going to use Desmos to graph T of T. Where would you guess the horizontal asymptote is? The horizontal asymptote is question mark. Okay. So if we use Desmos, one thing, I had to use the exp function. And so down in the bottom, right, you've got your functions. And so I'm going to plug in my 70 and then plus 90 and then times the functions. And over in the miscellaneous, there's exp. And that's pretty typical that we have to clarify that exp, because in programming, right, you can define any variables. And so you have to have these reserved functions. And so E is kind of a common variable that we use. And so you have to specify that exp is the one you want. So the exponential function, which means that we have to wrap it up in brackets. So exp of, and then whatever you have in the power goes inside those brackets. So we've got negative 0.1 x end bracket. It didn't like that. Or maybe it did. I just have to zoom out. Great. So if we click on this line here, it'll tell us that it crosses the y-axis at 0, 160. 160, that was at the initial time 0, right? That was the temperature. And then we all understand that the coffee's not going to get warmer as you put it out into room temperature. It's going to cool off, right? And so we've got this behavior where it's decreasing. And then, but at some point, it's going to kind of slow down, right? And so if I can just hold it steady there, right? It looks like around 70. And so it looks like the horizontal asymptote is at 70. So if I have to sketch this out, it looks something like this. This was at 0, 160, and then I'll draw here. This is at y equals 70. From the graph, we would guess the horizontal asymptote is at y equals 70, right? Y equals 70 degrees Fahrenheit, which I don't know about Fahrenheit, but reasonable to assume that that's the temperature of the room. Which seems like it might be the temperature of the room. Okay. And then finally, part C, find and interpret the behavior of T of T, the behavior of T of T as T goes to infinity. We expect our answer to be 70 just by the graph, right? Or roughly 70. And so we kind of have a good idea of what to expect. And so if we take, as T approaches infinity, right, we've got T of T was 70 plus 90, right? E to the power of negative 0.1 times T. Or I won't have it in brackets, I guess. There. So when we're talking about, okay, as T approaches infinity, I want you to think about, okay, so T is going to get very, very big, right? T is multiplied by negative 0.1. So now we've got a very, very big negative number, right? And so what we do is we say, okay, well, because we're just trying to get an idea, right? There's no math that we can do with infinity. And so if we plug in infinity for t, right, we get this very big t, but then we multiply it by negative 0.1. And so even though it's 0.1, right, times infinity, it's still going to be huge, but negative, right? And so what we have is times e to the power of a very big negative. E, when x is a very big negative, this is where it comes in handy to know, okay, well, what does the exponential function look like, right? And so e to a very big negative is sort of 0, right? Or you can think about it as, okay, well, a very big negative is e to the negative very big number, which you could rewrite as 1 over e to a very big number. Either way, it doesn't matter. It's going to go to 0. And so we've got 70 plus 90 times or a very small number. Very small positive, I guess. Roughly 0. 70 times or plus 90 times roughly 0 is roughly 70. So t of t becomes roughly 70 as t goes to infinity. We're not going to do a lot of this kind of limiting behavior, so this is kind of leading us into limits for calculus, but it is good to have seen it once or twice where you're just kind of imagining, okay, well, that becomes very big and this turns very small and then it goes to 0 and then we're done. Any questions? No? You've been troopers today. See you guys on Thursday. I'll be around for questions about the assignment, though. If you have any, let me know. Otherwise, see you later, Gators. Bye, guys. Or bye, Jared, I guess. It's just Jared.